Okay, we will directly start. Okay, this is the what I was mentioning to you last class, that from now on we will be dealing with forward flight. See, the forward flight has more complexities, particularly with regard to the aerodynamics, and because of that the structural motions or the blade motion occur, and that again influences the aerodynamic loads. So, as a result, this problem becomes a, you can say, the aeroelastic problem. So, you cannot treat forward flight. So, we have essentially divide the disc into two regions. One region we call it advancing side, that is because the oncoming flow and the rotational velocity, they add together. So, if you look at the just a simple expression for the velocity, this is omega and this is my oncoming, that means helicopter forward flight, and please remember this is on the rotor disc. So, slowly you will add more and more complications. Now, this angle is psi, always it is measured from the rear, this is a standard from the rear of the disc, and at any section you will have omega r, this is the rotational speed, but this velocity is here, this is psi, this is also psi. So, net oncoming flow velocity is omega r plus v sin psi, omega r plus v sin psi. Now, you know that psi is varying because psi is omega t. So, immediately it tells me my oncoming velocity is time varying, but what is the frequency? It is basically the rotor angular velocity omega t. Okay. So, we always say the variation, this is a terminology, once per revolution, that is called 1 per rev, because the variation is once in a revolution. Okay. This is a 1 per rev, that means it represents the rotor angular velocity. Now, this, if you use the simple aerodynamics, like last time I told you, lift per unit section, you take half rho u square card CL, lift per unit area. This u is this, of course, there are other components. Immediately you will see this is a square, so you will have second harmonic sine square psi, which will become cosine. Okay. Now, you see slowly you are adding time varying quantities in the system. The moment you have time varying quantities, you will start having, that is why this periodicity cause periodic aerodynamic loads, and that will cause blade response, because you have a time varying load. Time varying load acting on a beam, it will make it vibrate. Okay. So, blade response is the cause of that, and this will cause vibration. Now, there are other two aspects which I have added, stall and reverse flow. Why the blade should stall? Blade means not the entire blade will stall, some sections will stall. Why they have to stall is because you see in this disc advancing side my velocity is additive, that means oncoming velocity is more. So, if the velocity is more, I am going to get a more lift. When I get a more lift, one side is having a higher lift, the retreating side is having a less lift. Okay, you have to balance. That balancing is done by changing the pitch angle of the blade. So, theta, you remember if we started earlier, collective 1c cosine psi plus theta 1s sine psi. Please note, this is my blade pitch. Okay. Now, you see what is your CL? Lift curve slope into angle of attack. The angle of attack has this as the component. That means CL is also time varying. You see, now CL will have, if you simplistically say, this is the one harmonic. Now, u square 2, you multiply, you will have higher harmonic, more and more. So, you will have more and more components coming in, you follow. Now, that is why you see the swash plate mechanism which is introduced in the blade is essentially to change the blade pitch angle once in a revolution. Please understand, that is why 1 per rev, you do not change 2 per rev, 3 per rev. Later we will see there is something called a higher harmonic control that will come maybe towards the end of the course, just for a description that part. Now, you see this is varying. Now, by in the advancing side, I make this angle small, usually it becomes negative, okay, but do not bother, this is small, and on the retreating side I increase this, in the sense increase means this component, okay. When I do that, collective is always fixed, okay. Suppose if this angle is negative, that is theta 1s is minus, what will happen? Advancing side it will subtract, retreating side sin psi negative, so that will add. So, you find I increase my pitch angle on the retreating side, that is again in once in a revolution. You are deliberately changing the pitch angle once in a revolution, and you will find at some particular speed you may start having, because the pitch angle required may be a little bit more. So, you find some sections will stall, but the stall is not that it will suddenly drop, the stall will happen, and again when it comes the flow will get attached. So, it is like flow detachment, attachment, detached flow, attached flow. This is what will happen in that, and that is why it is called not static stall, this is actually a dynamic stall condition, okay. Then you have reverse flow. Reverse flow, I will just mathematically show it here. That is this omega r v sin psi, on the retreating side omega r is coming this way, v is coming this way. So, they try to subtract, because sin psi is greater than 180 degrees. Okay, so it will have a minus sign. So, some regions the flow will be coming, this is omega r, please understand, this is because of the motion your, this is omega r, okay. This is V sin psi. So, if omega r is small, the flow will come from the trailing edge towards the leading edge, and that is called the reverse flow region. Now, that region can be shown mathematically to be a nice circle, okay. That will be like this. It is a perfect circle, okay. This is reverse flow. How the circle is made is, we have to, the boundary of the circle, this is omega r plus V sin psi is 0, that is the boundary, okay. Beyond this, omega r is large, below this omega r is small. Now, you take this angle to be phi, okay. Now, psi is 270 minus phi. So, you will have omega r plus V sin, please understand I use the same symbol phi, do not get confused, this is just for denoting, okay. Then this is nothing but because sin 270 is minus 1 and cosine phi. So, this will become omega r plus V cosine phi is 0, and cosine phi is omega r over V, right. So, you will write, no, is there a plus sign or minus sign? Sorry, I am sorry. So, cosine phi is right, is it correct? Huh? Hey, is it right or wrong? Huh? Check it, okay. Now, in a right angle triangle, you will find cosine phi is nothing but this divided by this, okay. If you take a circle from one end, because this is the diameter, if you take, you know that this is always 90 degrees and this is my phi, okay. So, this gives me the condition for the boundary, okay, and that boundary is nothing but when phi is 0, omega r is V, okay, that means this point, that is the radial location where omega r is equal to the oncoming, that is the helicopter velocity, that becomes your diameter, and then this is when it is at any other angle, this is the radial distance, okay. So, omega r over phi represents, actually omega r over V represents, this is nothing but a right angle triangle. Therefore, this becomes a perfect circle, and the reverse flow region, if you want to non-dimensionalize, that is normally done, because it is never written in this fashion. I will just show. You divide by capital omega r, okay. Then what will happen? Omega okay. This is r bar. You call it approximately. I am saying approximately. This is a new symbol that is used, which is mu. Okay. R bar is mu okay. That means you immediately know the reverse flow. This is R bar, this, which is nothing but non-dimensional velocity. Okay. Now you see the reverse flow region actually will increase with forward speed, because if V increases, mu is increasing. That means this region, as you keep on increasing your helicopter velocity, that will become bigger and bigger and bigger on this side, retreating side. So, you know that you will get the lift only when the oncoming flow is towards the leading edge, not when the flow is from the trailing edge. Okay. Now, that region is getting reduced. Okay. As you keep on increasing your speed of the helicopter, the reverse flow region will become bigger and bigger and bigger, because it will occupy large. This is one of the reasons. I won't say this is the only reason. This is one of the reasons why helicopters cannot fly very high speed, because you can't make the entire retreating side not generate lift. Okay. Because please remember, the flow is highly complex. In this zone the flow is coming like this, here it is coming like this. Okay. The net relative flow, net air velocity. So, you have stall problem, you have reverse flow problem. So, what will happen is, if this region becomes bigger and bigger, you need to generate lift here, which means you have to increase the pitch angle. That means, if you keep on increasing the pitch angle, you may stall. So, you see these are restrictions. That is why helicopters cannot fly, even if you put a powerful engine, it just cannot fly at any speed. This is only one of the reasons. I am not saying this is the only reason, because there are several reasons. Because what will happen if you keep increasing your helicopter velocity, advancing side velocity is omega r plus v sin psi, and that velocity is also increasing. That means, you are increasing the Mach number in the advancing side at various sections. So, as you keep on increasing Mach number, you may get into transonic zone, you may start having higher drag, and there are some drag divergence, everything, because the drag it will be up to some Mach number, it will not change much, then suddenly it will start going up. That means, you will start having drag divergence, increased drag, that means you need to have more power. So, these are all the problems which you start facing in forward flight. Okay. Now, we have expressed the basic complexities. I would say the basic complexities. We have not gone to inflow yet. We are only looking at the flow in the rotor disc. Okay. Inflow comes next, because inflow is very important. That is why usually it is mentioned these are complex. I will show on diagram then later next. So, because of all this, one of the critical thing which is blade response to be included in all load and power calculations. Okay, these are important, because blade response you cannot avoid. We have not talked about blade response here till now. I am only purely from what we know omega r and v, that is all. What do I mean by blade response? Okay, blade is a beam. The beam can bend up and down, beam can bend this way also, and then it can have elastic twist, only these motions. Of course, centrifugal force is pulling, please understand, that is always there. So, you have these motions are blade motions. So, you have to have a model for the blade, that is I would call it a structural model, very simplistic. So, we will start that whole thing as we go along the course. I will introduce each aspect, but simplistically, please understand, because it is still a very complex problem. So, how do people treat this at the preliminary level? Okay. Now, we have to have a model for the blade, number one, please understand. Now, how do we idealize? So, for the course we will idealize in some particular fashion, highly simplified, please understand, okay, but meaningful. It is not that you simplify to a large extent that it becomes meaningless. Okay. You simplify which is reasonably meaningful, okay. And then we need to get inflow. Inflow is another complication. So, I will show the next thing. What is the general flow? The picture is okay, right? I just put what all I said as a the blade schematic diagram of flow structure of a helicopter in forward flight. The blade will start giving vortices, because vortices is basically disturbance. You know, the lift you have a vortex coming out, and then they will come, they will hit the blade which is coming behind. In the sense they will all come interact. This is, they call it blade vortex interaction. And then at the tip you will have a transonic flow, then the hub is there, hub, and then where the engine deck, and in forward flight that will start giving its own disturbance to the flow, and this flow will all go hit the tail, okay. And the wake with basically the disturbance from the rotor and the fuselage, they hit the airframe, and then wake and then tail it will interact. So, you will have all sorts of aerodynamic complexities, please understand. Now, you can't treat everything even today, okay. So, what do people do in industry? Of course, the work is still going on, you know, people will keep on doing. It is a very, very complex structural dynamic, aerodynamic interaction problem, okay. We will make it highly simplified, okay. How do we make it simple is, first some more complexities I will show. This is just to tell you the wake which some of the models which people use in their studies, okay. This is the rotor blade, and you will have tip vortex, you will have shed vortex. Shed, so there are two words, please understand, trailing and shed. These are two different vortices, trailing vortex, shed vortex. If the circulation is constant, then there is no span wise variation of the circulation on the blade. So, you have your horseshoe vortex which you have learnt in your aerodynamics course, that will come out from the tip. Okay. That is your lifting line theory. It says that my circulation is constant, it comes out. That is called the trailing, because it trails and that vortex will be like this. In the sense, usually I will draw from the point of view of clarity. Suppose you take a simple wing, just a wing. This is okay. This is trailing. The trailing will be in this direction. This is trailing. Okay. Then what is shed? Shed is, suppose if this circulation varies with time. Okay. Please understand. If it is a span wise variation is there, you will get the, please understand, this is constant gamma, you will get only here. Suppose if the gamma is a function of span, you will get what? Like this. Okay. You may get all of them are trailing. This is span wise variation of circulation. Suppose if circulation is a function of time, then you will have like this. These are shed. Okay. So, you have shed vortex, you have trailing vortex, but usually there are a lot of assumptions made. For the simple, first I will say I do not bother about the shed vortex, good. I will only worry about as though the loading is uniform, only tip is coming out. That is a uniform loading case. Okay. This is how assumptions are made, and based on that assumptions they try to get the effect of that wake on the inflow, which is very approximate. But then people will update their models to include complexities one at a time. Okay. So, I will show some pictures of the approximation that is made is my circulation is constant, it does not vary with span. Please understand, this is what is called uniform loading. That means what? You will have only the tip vortex. So, the tip vortex in the case of hover, it will come below because it is pushed down. Okay. Only tip vortex, I do not consider anything else. But when you go to forward flight, please understand what will happen is the rotor disc is not stationary, it is moving. When it starts moving, whatever it leaves, that wake is going back, and that will go, we will take it like this, as though this is pushed backwards. Okay. And I have indicated one angle which is chi, that is actually wake skew angle. Okay. That is just to indicate this, how my wake is there. So, this is called the wake skew angle. Okay. Do not worry too much about this, because this will come later when we try to describe certain things. This is wake. Okay. Just, and I am taking as though this is a cylinder, skewed cylinder, and on that face I have the vortex. Now, I may use actuator disk theory. Please understand, actuator disk says what? I have infinite number of blades. That means, I will have enormous number of blades, my wake in hover is just a cylinder. Okay. In the case of forward flight, it becomes a skewed cylinder. Now, the skewed cylinder gives its own problems. People have derived this with the skewed cylinder, how the inflow is calculated. We will not get into that part now. I am just wanted to give you the complexity involved in this. Now, I will show a few pictures from purely aerodynamic thing, whatever I said, because this is interesting to have a look at these pictures, because then you will understand the wake. This is one picture. See, this is when you start an aerofoil, because there is no lift. When you start means what? Your velocity is increasing. That is why the vortex theory, whatever you use, that lifting line theory which you call it, it's a very, very powerful technique, because as a observation, when the aerofoil starts from rest, there is no circulation. That is why we call it irrotational field. Those of you who are familiar with fluid mechanics, I am just saying irrotational fluid. Then what happens? A vortex starts from the trailing edge, and this is the starting vortex. You see, the direction is like this, and there should be another bound circulation which will come over the aerofoil. One is the shed. Now, this is what is shed. You understand, because initially there is nothing, so it is shed. When you shed it, what will happen? Because of the oncoming velocity in aerodynamic thing, this gets taken back, and the effect of that vortex on the aerofoil is, you say, 0. So, I have only a bound circulation. Okay. That is why you say gamma. In the lifting line theory, you draw what? Simply take gamma, rho u gamma. Only thing is you have to, this is, okay. The effect of all, you study this only in getting a induced angle, okay, induced angle. This gamma, that is why I am saying when you start, you will have one. When you stop, you see, one is this, another one is this. Now, there is no more, that gets shed. So, when you start and stop, this is the picture. So, when the lift is also varying, you will have all these things coming out, but this is attached flow, please understand. Once you have detached flow, things are much more complicated. Okay. Now, I will just show a few more pictures. You see, when the helicopter is hovering, this is taken in I think in a morning dew or something like that. Okay. So, you can see distinctly the tip vortex in a hovering helicopter. Okay. See, they are coming. Now, this is also, there are some pictures which are actually made in flow. That is how wake structure looks. This is on a lab. See, this is the blade, how it sheds, and how the wake contraction. These are all flow, I would say, visualization. After that, you use a theoretical model. Okay. Now, the same wake structure which I showed here, if I put it, this is in the hover case, if I start moving forward flight. So, they again took some pictures. That is a very interesting picture. I will show the diagram. It was actually a flight test. It was a flight picture, the bottom one. Okay. You see the flow, because something was pushed, some smoke, how the smoke goes in and then goes back. It is not pushed down. And the similar picture which is shown on a small scale thing, the smoke is given, the flow is in this direction, please understand, and this is rotating. Now, how the vortex which gets released from the tip in the front, how does it move? You see, it goes up and then comes inside. You follow? Now, all these are complex phenomena, but you see, the reason I wanted to point out the top one is that is one of the reasons till 80s the results between theory and experiment, they are quite far away. This is the rotor, this white streak, okay, white line. See, the vortex, the flow goes like this. It is not that it goes. What we assumed, it is a cylinder like this. You assume, you saw that, but actually it goes up and then down. Now, you need to capture all these things, which is still a difficult task. So, there are models which are used to approximately capture, please understand, these effects. Okay. So, in this course, what we will do is, I will introduce briefly some of these approximations which are used, and the gross approximation is what we will use in our calculation. Okay. And so, now with this, the small background on the flow in forward flight. Okay. Because forward flight is a highly complex problem. Very simple. I want to get the inflow at the rotor. I have a very complex flow, but I am going to say, hey, let us not worry about those things. I want, like you said in hover, you applied the momentum theory and you predicted the inflow through the rotor disc. Okay. Similarly, you apply the momentum theory to forward flight. Okay. But please understand, I will not write all those various things. This is all simple extrapolation of what was there in the hover momentum theory, because some proof here, it is only from analogy to fixed wing. Okay. This is where the ingenuity or whatever you may call it. So, there is a lot of approximation even in this. Now, what is that approximation? How the inflow? Simple, as you, this is my rotor disc. Okay. My rotor disc, for the sake of general, the disc is moving forward and up, please understand. It is not just going only horizontally, it is also flying up. So, you will have, that is the reason why I gave this is the velocity of the oncoming flow. Please understand, the velocity of the oncoming flow to the rotor disc. The rotor disc is not moving like this, rotor disc is moving like this, okay, up. Now, this is, you divide this into component 1 parallel to the rotor disc, another one perpendicular to the rotor disc. So, V cos alpha, V sin alpha, okay. And then I have put thrust, because the helicopter is holding, this is a steady velocity, there is no acceleration, it is moving steady. Thrust is up because it has to support the weight of the helicopter. So, therefore, for supporting that, there should be an inflow, okay. But that inflow is actually normal to the rotor disc, normal to the rotor disc, okay, because I am pushing the air down, so I am going up. Again, simple far field, you take it as W, and that W you take it, momentum theory tells you W is 2 nu. So, whatever happens, the inflow at the rotor disc, the induced velocity at the rotor disc, W is 2 times that value, that is all. So, these are all from, I am just, please understand, extrapolating from hover momentum theory. Okay. Now, what is my thrust? Thrust is, momentum theory tells me m dot mass flow rate into change in the flow, okay, 2 nu. The change is 2 nu. Initially 0, here it is changed to 2 nu. Now, what is m dot? Okay. M dot is flow through the rotor disc, mass flow rate, but this is where the approximation u, where u is, because you always normally you think that the velocity, because this component v cosine alpha is parallel to the disc. What is flowing through the disc is v sin alpha plus nu, okay. But you take in defining mass flow rate, this is based on Glowat, okay. He said that use u square as okay. Now you may say why, the question will come, the why, how, what comes from the limits of this expression, that is whatever I showed here, the limit of that expression when alpha is 0 and alpha is 90. Okay. When alpha is 90, what happens? It is a climb. Alpha is 0 is high speed flight, okay, high speed flight of some disc, okay, because these are all actuator disc, mind you, this is not a rotor system, because the momentum theory assumes it is an actuator disc. In the high speed flight, I have to get an expression. Please understand, this is how the whole logic goes. For the lift, we should look, because you know from the lifting line theory for a elliptic wing, in a horizontal flight, you will get the lift, you get the drag, induced drag expressions. Please understand, that is how it was brought in. I will explain to you later how that whole thing came. Now you see, you are getting an expression if you use, let me put it that way. So, I will write it here, rho A, sorry, u dot is all right. So, thrust is, I will write it, thrust is 2 rho A nu v cosine alpha whole square plus v sin alpha plus nu square, okay. A is the area of the disc. If alpha is 0, right, 0 means I am flying like this, then this will become limit alpha is 0, it is a very high speed flight, and you can represent this entire expression because nu is small, because V is very large, nu is small. So, this whole thing will be just V under root of V, okay, under root of V square. So, that becomes V. High speed flight alpha 0 thrust is 2 rho A nu V, high speed, okay. We will try to get that from fixed wing theory, okay. Then you will see, oh, this is the reason it is put in. Suppose if you say I neglect this V cosine alpha from this whole expression, high speed flight, what will happen? This goes up, right? Alpha is 0, this is gone. This is only nu square, that will be nu. So, you will have 2 rho A nu square. This is same as hover, okay, when alpha is 90 or a hover is V is 0, okay. You find that that comes like a hover theory, it does not make sense, okay. That is the reason Gloat, that is why he wrote this, you take this expression. Please understand, now you see my inflow is constant over the rotor disc, it is a constant, it is not varying along any radial location. Is it clear? Now, in the straight vertical flight, yes, it matches. When alpha is 90, this term goes, this is V plus nu, you put it here, that is nothing but what you got for hover. So, the two extremes, in hover it matches, in high speed forward flight, how does it match? So, that I will just briefly, before I go, I thought I will non-dimensionalize these quantities. These are the new expressions of the same velocities. We define, please understand, we define V cosine alpha over omega r as mu, which is called advance ratio. Okay. And then the other term, which you call it as the total induced velocity, because I would like to use it total induced velocity, because it has two components. One is due to V sin alpha, that is due to the flight itself. Another one is the induced component. So, this we will call it lambda, which is a, sometimes you loosely use inflow ratio. Okay. So, you can call that as lambda is V sin alpha plus nu over omega r. You may take this term itself, okay, you divide by cos alpha, divide by sin alpha, then this, sorry, divide by cos alpha, then V cos alpha over omega r will become mu. So, you will have mu tan alpha plus lambda I. Okay. So, mu tan alpha lambda I. Okay. Now, directly go back to the original expression. Thrust is, you know, Ct, okay, and you will see how do I get inflow, because in the hover case it is square root of Ct by 2. Here you will have, you use this expression non-dimensionalized, divide by rho, you will get that expression of lambda I. I will just briefly write that, because you can non-dimensionalize. Lambda I becomes, lambda I is nothing but nu over omega r. This you obtain from this expression here, from here. You divide everything. Okay. So, this is T over 2 rho area, right, because you have to divide another omega r also. So, you will have V what cosine alpha square plus V and divided by omega r, you will have a omega r. Okay. If you want to non-dimensionalize, what you will do? You divide by rho, pi r square is area of the disc and omega r whole square. So, you will also divide this by same rho a omega r whole square. Okay. So, rho a will go up, one of the omega r will go inside, another will cancel out with this, leaving behind now your lambda I becomes C t over 2, what is that? There is a 2 root V cos alpha square is mu square. This is lambda square, or you may write it as mu tan alpha plus lambda I whole square. Now, you see this is my inflow. Now, this is not that easy to calculate, because if you want to calculate, first of all you must know mu is advance ratio. Now, you understand this is what we use as a terminology in this course, advance ratio. Advance ratio means loosely forward speed by tip speed. Please understand, loosely forward speed by tip speed, because you are neglecting that cosine alpha, but precise definition requires V cosine alpha over, but normally alpha is very small angle. So, it does not matter, you take it as forward speed by omega. Now, this is the mu which I mentioned earlier in getting the reverse flow diagram, it is the same mu. Okay. So, if you increase your, now the question is, if you want to get this, you need to know mu, you need to know alpha. That means the orientation of the disc with respect to the oncoming flow, that you must know. And the next part is, this is a iterative procedure. Lambda I is here, that is what you are getting here. Okay. Now, this is not very easy to obtain, you have to write a small code, because you have to solve it iteratively, whereas you see in hover it is very straightforward. Okay. Now, forward flight, the moment you go forward flight, all come, and this inflow is a gross approximation of what really happens on the rotor disc, because you have assumed that it is constant over the entire disc. Please understand, it is constant, it is uniform everywhere, nothing, but this is a gross approximation, and this is still used. Okay. It is not that this is not used, it is still used even the research level, because this gives pretty decent result. Of course, we add more complexities to that, rho a nu into V, right. At what speed it is valid. Okay. We will see, it is more than, I will say, non-dimensional 0.115 onwards, you will find that is fairly all right. Mu advance ratio 0.15, that's fairly good. 0.1. I'll show the diagram, I'll prove it. But first of all, you have to know how you got this. Okay, I thought this is a very interesting thing, because one is you, okay, Glover said take this, okay, everybody took it. That's one thing. Another one is, hey, what the hell, because somebody says you take it means you take it. You don't take it, you ask questions, why? Then you say one end it should be valid. Any expression you derive, it should be valid at least at the extremes. In between, okay. So the extreme case of hover, it is valid, hover and vertical climb. But in forward flight, how? So that comes from essentially, because it is not there, it is in my notes, I will show you. This is a small, it's an interesting thing. I will go there, okay? Is it okay? See, you know, fixed wing theory tells you induced drag coefficient, okay? CDI, because fixed wing, please understand, I am directly jumping to, this is, you all know, pi aspect ratio, okay, because those of you who have done aerodynamics, you will know this, okay. If you have not done, take it, because then you can read a aerodynamics book and then you say, oh, okay, for a elliptic wing loading, say minimum, because this is the minimum induced drag, that is what elliptic loading, all those assumptions, then you get this value. Now what you do is, you take this, you multiply by, what is CL? CL is nothing but lift coefficient of the wing. Please understand, this is a finite wing theory. Okay, this is a finite wing theory, because aspect ratio is there. Okay, you remember this, or okay, now you multiply both sides by half rho v square s whole square CL square divided by, you do that, half rho v square s, one of the values I am taking, pi aspect ratio is, you know that if it is a B is span, so you will have, okay, this is aspect ratio, and then another half rho v square s. I am just, now this term is nothing but the force, which is, I am going to write it as, maybe I erase here, because the board is, I will take one of this term, take it here, okay. If I take this term and then put it here, half rho v square area CDI, that becomes the drag force, okay, induced drag force. So I am going to call it as DI, induced drag force. Okay, this is nothing but, I am using the helicopter terminology, thrust, because area into CL is thrust T square, and in the denominator it is going to have what, half rho, this S will cancel out with this S, okay, you will have what, pi b square, b is the diameter. So what you do is, you divide by 4, multiply by 4, okay. when you do pi b square over 4 is area of the, because b is the span, that is 2r. So, that is going to be the area of the disc. So, you will have, and the 4 and this will become 2 rho area v square. Okay. Is it clear? Now, my drag force, induced drag force is this expression. Okay. What is my power? Okay. Induced power. So, I let me erase this part. Okay. What is induced power? Induced power thrust into nu. This is also equal to di into, because di is the induced drag force, into the velocity. So, di into v. Okay. Now, you want to get what is nu. Okay. What is the induced velocity? You equate, that is nu becomes di v over, okay. This is the induced velocity. Please understand, I am relating rotor wing kind of a thing. For the rotor, this is the induced power, T into nu. For the wing, this is the induced power, because this is the induced drag into the velocity, you are dragging it in the forward flight. Now, I want nu is di v over t. Now, you know here di over t. Okay. You can substitute here, di over t will become what? T, because over 2 rho a, this v will cancel with one of the v, right. So, you will have, in other words, thrust is high speed. Okay. You follow? So, you see, but this is nice jugglery, but what we started off with a large aspect ratio, minimum induced drag, etc. But the aspect ratio of a wing is what? Aspect ratio of the wing, there you take it to the large aspect ratio. Here, if you take aspect ratio of a rotor, rotor aspect ratio is what? Rotor aspect ratio will be just b square, that is nothing but 2r, okay, over pi r square, which is 4 over pi, which is 1.27. This is the aspect ratio of a rotor. So, you say this is too small. That is why your inflow, that is inflow is that nu, cannot be assumed to be uniform everywhere. There will be lot of variation, because the aspect ratio is too small. So, inflow cannot be same. So, it has to vary quite a bit, that is all. That is all this statement says. But Glover got this, hey, this is a nice relationship. So, at high speed, the rotor behaves like a wing, just a fixed wing. You understand? But with considerable variation in the inflow, but it is like a wing of that size. Is it clear? That is why you will realize, I will show some of the results which we have generated here, maybe as we go along. That was a PhD work, which is a very complex aeroelastic analysis. You will find you use any aerodynamic model as you go to high speed. Now, I will answer your question later. As you go to high speed, you will find they all come close. You may use different models in gross estimates, but not in loads. Vibratory loads, please understand, when you look at the vibratory load, it varies with what theory you use. When it is flying that equilibrium or trim condition, you will find does not matter. Okay? That is the beautiful result. That is why I am saying this is all from, you relate the fixed wing on one hand, but you have the momentum theory on the other hand from rotary wing, and then you simply say, hey, I have to bridge between hover condition to high speed flight, and that is the reason the net, that is in defining the mass flow rate, you add V cosine alpha and V sin alpha. That is the reason. Okay. Now, we will solve, because I thought I will take next class, which will your answer will become clear, because this is a very neat expression. Okay. But only question is, at what V you can start using this, you can start using it approximately. Okay.